Hi, good morning. Today we are going to start our third module, and the first session is the ninth chapter. Okay, the fundamental theorems and the basic method. Actually, this chapter contains most of the result in our functional analysis. Okay, like bare category theorem, open mapping theorem, closed graph theorem, like all theorems comes under this chapter. Okay, so now just to recall what we have discussed in our earlier classes, these portions represent only a revision of our previous topics. There is no need to write all these things in your book, just for as a preliminaries we are discussing this. Okay, so a linear space, we are considering a linear space L over the field of real numbers or a field of complex numbers. So L represents a vector space or the field of real or complex numbers, and we define a norm on this one, and we are considering a normed space. Okay, and let it be X. X is L with this norm. Okay, and we assume that X is complete linear space, and a complete linear space is called a Banach space. Now a linear map F from X to R is called a linear functional. Okay, the set of all linear functional is denoted by X hash or L hash. Okay, and the subspace of X hash consisting of bounded linear functional, we call it as a X star dual space, and this is a normed space with a norm of f equal to supremum x not equal to 0 modulus of f of x by norm of x. The dual space of any normed space x is a Banach space. Now L is the linear space of all bounded linear map from X to Y. Then this is a Banach space if Y is a complete space. That is Y is a Banach space. Okay. We have discussed all these things. Now moving to our next result. These are some preliminary result. Actually this is about metric space. Okay. So now moving to section 9.1 auxiliary results. Just listen carefully. In a set M, we define a distance, okay, distance function to be a non-negative function rho of xy, non-negative function rho of xy, x comma y belongs to M, and which is called metric if it satisfies the following condition. The same metric you have studied in your real analysis. Okay, so rho of xy equal to 0 if and only if x equal to y, rho of xy equal to rho of yx, rho of xy plus rho of yz greater than or equal to rho of xz. I think you have studied like this. Rho of xz is less than or equal to rho of xy plus rho of yz. Okay. So this is the definition of a metric. Okay, the set EM with a metric rho is called a metric space. Okay, the set EM with a metric rho is called a metric space. Now, a metric space M is called complete if for any sequence xn contained in M such that rho xm tends to 0 as M tends to M comma n tends to infinity, then there exists a limit x belongs to M such that limit n tends to infinity rho of x and x is equal to 0. Okay. Now, actually, what is mean by completeness in our normed space? We are considering norm of xn minus xm tends to 0 as n comma m tends to infinity. This is what we have discussed. Here we are actually replacing and the complete space means every Cauchy sequence is convergent. Every Cauchy sequence is convergent means this is a Cauchy sequence, and convergence means it has a limit. Same definition here. Here distance function means rho of x and xm tends to 0 as m comma n tends to infinity. There exists a limit x belongs to m. Okay. That is limit n tends to infinity rho of x and x equal to 0. Clear. Same definition. Already we have discussed convergence and all other things in completeness in normed space. Now here we are coming to metric space. Okay. So in normed space, a space is complete. Every Cauchy sequence is convergence in it. Same result here. Okay, row of x and xm means this is in terms of Cauchy. Okay, and this converges to a point x, and that point must be in M. Next, for a subset of M, we denote A naught as the set of all interior points. Okay, and A closure is the closure. Same result as in our real analysis. Okay, interior points. Okay, now A complement means this complement of A. Now, actually, what is A closure? A closure is A union the limit point of A. Okay, complement means the point that is not in A. Now, what is A naught? The set of all interior points. Suppose some x naught. X naught is called an interior point means what? There exists an open ball there exists an open ball with the center at x naught completely contained in A. Then we call x naught is an interior point of A. Now what do you mean by a limit point of A? If you take any neighborhood of x naught, then this must contain at least one point of A. Okay, other than x naught. So these are the definition of interior point, a closure, and a complement. Now, a subset, this definition is very important. A subset of M is said to be nowhere dense. What is it called? Nowhere dense if the closure A closure does not contain any interior point. A is said to be a nowhere dense if closure of A does not contain any interior points. Okay. So if a set A is, there is a result. If a set A is, once again I am repeating the definition, a subset of M is said to be nowhere dense if the closure A closure does not contain any interior point. Okay. Next definition, next is a result. If a set A is nowhere dense, then for any open ball B contained in M, there exists an open ball B1 contained in B such that B1 intersection A is equal to empty. Actually, what is the meaning of this contains no interior points? A point x naught is an interior point uh, if you take there exists a ball interior suppose interior point of A, there exists a ball completely contained in A. Okay, so this is not an interior point means what? There exists an open ball not completely contained in A. Okay, so if you take any epsilon, then for every epsilon uh, there exists a epsilon. You can find there exists a point for every epsilon. There exists a point some p in A complement. Okay, such that p is in this epsilon form. Clear. Now the theorem says that, now result says that if A is nowhere dense, then any open ball B containing M, there exists an open ball B1 contained in B such that B1 intersection A is equal to empty. Okay. Note that what is B? B is an open ball. Then what is B intersection A complement? B minus A bar is B intersection A bar complement. Okay, and this is non-empty. B intersection A complement is non-empty. Now we are going to prove, suppose B intersection or B minus A closure is empty. We have to prove B intersection A closure is not equal to empty. So first suppose that B intersection A closure is equal to empty. That means B intersection A closure complement is empty. How we can write? We have A minus B is equal to A intersection B complement. Okay. So B intersection A closure complement is equal to empty. That means B is completely contained in A closure. Therefore, A closure contains interior point. Because why? B is an open ball means it contains interior point. Okay, which is a contradiction. Therefore, B intersection A complement is equal to non-empty. That is B intersection A complement is not empty. Note that the set B minus A complement is open and hence why how this we can prove this is non-empty. What is B? B is open. A closure complement. Complement of a closed set is complement of a closed set is open. Okay, so B open, this open, so this is also open set. This is again an open set, and hence there exists an open ball B1 contained in B minus A closure. For this ball, what is B1? B1 is completely contained in B minus A closure. This implies B1 is not contained in A closure. This implies B1 is not contained in A, because A closure is A union limit points. This implies B1 intersection A equal to empty set. Hence the result. Now converse part. Conversely, suppose that let A be a set in a matrix space M. Assume that for any ball, converse part. Let A be a set in a matrix space. Assume that for any open ball B subset of M, there exists an open ball B1 contained in B such that B1 intersection A equal to empty. Then A is a no-word dense. We have to prove A is no-word dense. Now, what is mean by no-word dense? A is a no-word dense if the closure A closure does not contain any interior point. So we assume the contradiction. That means A closure contains an interior point. Okay, suppose assume that A closure is not A is non-verdance. That means A closure has an interior point. Let X naught be that interior point. X naught is an interior point means, what is the meaning of that? There exists an open ball with center at X naught and that is completely contained in A. Okay. So this open ball, and I am denoting this as U. Okay, this U is completely contained in A. Now, for any open ball, by our definition, for any open ball, B1 contained in B contained in M, there exists an open ball B1 contained in B such that B1 intersection A equal to empty. This is our assumption. So, if you take any open ball B1 contained in U, and this B1 clearly contained in A because U is already contained in A. Therefore, B1 intersection A is actually then for any open ball B1 contained in U, we have B1 intersection A is not equal to empty because B1 is already contained in A. But that is a contradiction because we assume that this one. This implies A is a no-vertex. Okay. Now moving to next definition, a subset of M is said to be of first category if A is the union of countably many sets. Okay, this is of first category if A is equal to union I, Bi, where Bi's are nowhere dense for all I. If you can write A as a countable union of nowhere dense set, then we call A is of first category. Okay, a set C which is not of first category is called set of second category. Okay, a set C which is not of first category is called set of second category. Clear? F subset first category means A equal to this one, and it is of second category means we cannot write A as a union of non-word set. Okay. Now next is very important theorem, and this is called bare category theorem or bare Hausdorff category theorem. And the theorem is most interesting. Every complete metric space M is a set of second category. Every complete metric space M is a set of second category. Once again, I am repeating the statement. Bare category theorem. Every complete metric space M is a set of second category. Okay. So, to prove the theorem, we assume that every metric space is of first category and we will arrive at a contradiction. Okay. Assume that this theorem is not true. That is M is of first category. Then M you can write as M is equal to countable union of over dense set. Okay. N is equal to 1 to infinity. Union N is equal to 1 to infinity N where N's are over dense for all N greater than or equal to 1. Now we are choosing an open ball with radius 1 and that denoted as B naught as D of x naught 1 be a closed ball, okay, with radius 1 and center at x naught. Since the set A1 is given that A's are nowhere dense. Since the set A1 is nowhere dense, what is the meaning of that? Nowhere dense means A1 closure contains an interior point. Okay, so nowhere dense, there exists an epsilon 1 greater than 0. We are using the result. Okay, we are using this result. We have a set is nowhere dense means there exists an open ball. For any open ball B contained in M, there exists an open ball B1 such that B1 intersection A is equal to empty. We are using this result for in the proof. That is for any open ball or open or closed ball with radius 1 center at x naught. Since A1 is nowhere dense, there exists an open ball B1 equal to dx1 epsilon 1 such that B1 is completely contained in B naught and B1 intersection A1 is equal to empty. We are using that result. Okay. B naught is a closed ball. We can take, if you take B naught as a closed ball, if you remove the boundaries, then clearly B naught is an open ball. Okay. So B naught, if you take an epsilon 1 greater than 0, there exists an epsilon 1 greater than 0 and such that, and that ball you can denote as B1 as dx1 epsilon 1 such that B1 is completely contained in B naught and B1 intersection A1 is not equal to empty. Okay. We choose ball B1 to be closed and the epsilon 1 to be less than 1 by 2. We are choosing B1 as a closed ball and epsilon be less than 1 by 2 because this is actually of radius 1. If you consider any ball with the radius less than 1 by 2, then clearly that is completely contained in this set. Okay. Now we choose another ball B2 equal to dx2 epsilon 2 with the radius of epsilon 2 is less than 1 by 3 such that B2 is completely contained in B1 and B2 intersection A2 is equal to empty because A2 is again nowhere dense, therefore using, and B2 is an open ball, therefore using same result. Okay, for any open ball we can, there exists an open ball B2 such that B2 intersection A2 is equal to empty. Continuing like this, we get a sequence of closed ball Bn is equal to Bxn epsilon n with 0 less than epsilon n less than 1 by n plus 1 and bn plus 1 contained in bn and bn intersection an is equal to mth. Now we are proving xn is a Cauchy sequence. Let m and n m greater than n, then xn xm. This board we are considering boards like this. Okay, so clearly xm belongs to bm and bm is contained in bn. Bm is contained in Bn. As n increases, this Bi is okay. B1, B2, B3, B4 like this. So m greater than n means Bm is contained in Bn. Xm belongs to Bm implies Xm belongs to Bm implies Xm belongs to Bn. Okay, therefore rho xm xn is clearly less than epsilon n and which is less than 1 by n plus 1 and that tends to 0 as n tends to infinity. Therefore xn is a Cauchy sequence. Since m is complete, there exists a y naught belongs to m such that y naught equal to limit n tends to infinity xn. So x1, x2, etc. xn belongs to, where is x1? x1 belongs to b1, x2 belongs to b2, therefore x2 belongs to b1 also. Okay. Therefore limit xn also belongs to b1 because b1s are closed. Therefore y0 belongs to b1 and y1 belongs to b1 means y0 not belongs to a1 and x2 etc. belongs to b2. Therefore, limit xn belongs to b2. This implies y0 belongs to b2. As b2 intersection a2 is equal to mt implies y0 belongs not belongs to a2. Thus, we get y0 belongs to bn for every n and y0 not belongs to an for every n. This implies y0 not belongs to union n equal to 1 to infinity an. This implies y0 not belongs to m. That is a contradiction because the limit also belongs to y0 belongs to m. Okay. Therefore, M is say why not must belongs to M. Therefore, our assumption is wrong. That means M is of first category. Okay, that's all for today's class.